And hi, good morning, everyone. The topic I'm going to present today is the Vortex evolution and the fourth generation analysis on the floppy wing IMAV DelFly 2 in hovering flight. I'm here to present a paper on behalf of all the authors here, since I'm the fourth author in the list. And the first author is a master student, which was involved in our floppy wing experimental study from the University of Pisa in Italy. And as you can see, we have a lot of people from Asia, European, and Mid-Asia, so it's quite an international job here. And my name is Shuanghou Deng. I can understand it's very difficult for the European people to pronounce my name, but I promise you my name will be the most difficult part in my presentation. Let's go to the content first, and we have 4 parts here. First, I'll give you some brief introduction and the objectives of this research, and also the experiment setup will be discussed later on, followed with results and conclusion. I'm not going to talk too much about the DelFly ornithopters developed by TU Delft, since you have already quite familiar with this kind of flapping wing IMAV. The first DelFly one was developed in 2005 that we kick off a new project aiming to develop the new generation of micro aircraft. And later on, we optimized DelFly 1 into DelFly 2, which you have already saw the demonstration on Tuesday in our flight arena. And it's the DelFly philosophy that keep minimizing the DelFly, but without sacrificing too much flight performance of the DelFly. That's why we have DelFly Micro, built in 2007. The model for this experiment setup is DelFly 2. Okay, the overall objective of this such research is to address the aerodynamic performance of DelFly 2 in hover, the time-resolved fourth generation and the flow field topology on the wing and also in the wake of DelFly 2 in hover, also required by force balance and stereo PIV technologies. The Vortex structure was also investigated and then linked to the force production. Also, three-dimensional wake structure of DelFly 2 in the wake will be reconstructed by Kriging interpolation technique. The effect of some important parameters, such as the flapping frequency, aspect ratio, and flapping frequency and aspect ratio will be evaluated on their force production and also the flow structures. Here is the experimental setup of the data acquisition system. Then we can see the DelFly is connected, is mounted on a force sensor. It's ATI Nano 17 titanium, which is I think it's the smallest force sensor, the commercial force sensor in the world, and it's very precise, can resolve the force down to 0.14 grams without any filtering. And the flapping frequency of the DelFly 2 is controlled by a combination the Hall sensor and also speed controller signals. The center one is the control board, which was built, I think, several years ago by Christoph from the MAF lab. Later on, all the necessary information, that is the force in XYZ direction, and there are 3 moments. The current, the voltage directly fed to the DelFly 2 was acquired by a FPGA-based discretization system. In our measurement, the data recording frequency was set at 10,000 Hertz to guarantee we have enough data in one flapping cycle. This is the setup of setup for the PIV measurement. We have the vacuum measurement to identify the inertial to aerodynamic effect, and also 3 different PIV setup to capture different position of the DelFly 2. I will give a detailed introduction later on. We first go to the vacuum test. The vacuum test was performed in our high-speed wind tunnel of the aerodynamic lab. The maximum Mach number is around 11, but we're definitely not going to use the blowing part. The DelFly 2 was mounted up and down since we have support from the top. In the vacuum session, and the vacuum level is around 1 millibar. It's already near vacuum, and we think it's quite enough for identify the inertial to aerodynamic effect. This figure plots the power spectrum density of the thrust component, while the black and the red lines are the power spectrum of the DelFly in air and in vacuum respectively. As we can see, the first two flapping harmonics are really predominated by aerodynamics. That's why we decided later on to use a Chebyshev type 2 low-pass filter to filter the thrust, the current, and also the voltage by keep the two harmonics of the flapping frequency. And this one, we named it Setup 1 to measuring the flow structure on the wing. That the laser is from the front of the DelFly to directly illuminate on the wing. The wing was painted black to. Yeah, this one's super. Okay. This wing was painted black to decrease the reflection of the laser, and also we have 3 cameras on different position of on the side of the DelFly 2. I think this third camera, we use the middle one and this one for the stereo PIV, and this one is for the backup. If we lose some information there, we can find it from this third camera. During each case, the 6 images are captured by a 300 recording frequency, a double frame recording frequency of the camera to guarantee we have enough flapping cycles for the later ensemble averaging. Also, a CFX fork generator will generate the water glycol-based particles with a mean diameter around 1 micrometers as the tracing particles. In the post-processing, the LaVision David 8.2 was used. And also in the measurement, we used the LaVision Type 30 calibration plate to calibration in the first. And also later on, we used self-calibration to correct the misalignment between the laser sheet and also the measurement plate. In the post-processing, we used the image integration was performed by multi-pass stereo cross correlation. As we can see, first measurement, the field of interest is around 21 centimeter by 21 centimeters, and the different position of the laser sheet from the 2 centimeters from the root and until, I think it's until 16 centimeters outside the wing. The second setup that is aiming to measure the force, measure the Wick topology along the streamwise. Also, we use this 22 by 22 centimeter field of interest and the same position here. At the second setup, we measure the Wick topology along this spanwise position. It's from 1 centimeters after the wing until 21 centimeters in the back. Well, about fourth generation of the DelFly 2, here we plot 2 periods of flapping cycles. The green line here is the phase angle of the upper wing of the DelFly. We can see it's not really perfectly symmetric between the in-stock and out-stock, which we think is the interaction between the wing to wing during flap. It needs more time to peel. And also, we look at this is the thrust generation. We have 2 thrust peaks involved in one flapping cycle. The higher one occurs at the outstock, is after the middle of the peel, and the lower one is at the middle of the in-stock. Now, this image is from the setup 1, is on wing measurement. This black period is due to the laser sheet is blocked by this wing, but still we can have some useful information from this one. Here we have two counter-rotating vortex pairs, which is generated by the previous collapse motion. And here, also another pair of counter-rotating vortex are going to shed at the trailing edge. Here the angle attack is very slow. That's why we have this very small thrust generation. When we move back, this two vortex is already shed from the trailing edge, and since it's hovering case, that means it's without coming free stream velocity. This two vortexes is quite stable to stand here. When we keep going back, it's at the beginning of the outstroke. That this two shedding vortex from the trailing edge travels so slowly because there is no wind speed, and this two counter-rotating pair is going to be disappeared. Going on, that we can see a huge vortex pairs on both upper wing and lower wings that bring a much more suction part on the wing. That's why we have a peak here for the thrust. Also, it's going on here that the vortex is starting to paving around the wing. It brings more thrust also. Here we have second one that we can see the shedding of these two vortex. Also 7, 8 different. It's quite a complex vortex structure. Yeah, this a weak measurement result is from the setup tool that we put the laser sheet along the streamwise after the DelFly wing. Then we can see the shedding of these vortex pairs alternately generated when it flap. The top one is the outstroke, and then the bottom one is the in-stroke phase. I'll show you a video here to see. It might be much more clear. That during the flapping, that's the vortex. The counter vortex pair was shedding alternately in the outstroke and also in the in-stroke. We can see a clearly jet flow structure here. That's because of the flapping wing and also enhanced by the induced velocity of the counter-rotating vortex pair. Later on, we use a 3D topology Kriging regressive with local area estimation to reconstruction the 3D weak topology after the DelFly wing. Here we have this Kriging interpolation function in Bayes framework. The advantage by using the Kriging is we can work with abstract data, and also by coupling the local error estimation, we can incorporate the measurement uncertainty in this interpolation. In our measurement, the signal-to-noise ratio in stereo PIV was used as the error input, and also we used frequency domain sample diagrams to limit the computational cost. By performing Kriging interpolation from the data of setup 2, then we get this structure here. You can see this is an in-stroke structure, which was shed after the in-stroke. And here we have this one. It's not really clear. It's like arc shape, which is shed from the previous outstroke. And also here is a movie about the shedding of the vortex. Now we can see there are 3 predominated swirling vortex structure. Here we name it U-shape. It's the in-stroke structure shed from the wing. And here we have the outstroke, this arc shape shed in the outstroke. And later on, we also evaluate the effect of wing aspect ratio. The standard wing we named here as TD is the normal wing on DelFly 2 with 140 millimeters, have a half wingspan. And we keep this one keep the chord length stay the same and also the tip length stay the same. We only increase the span wise from 40 centimeter to 16, then back to 12. The harder means the high aspect ratio with different error as an abbreviation. Then we can see the force generator here is also plot in 2 cycles. Then we can see from this graph, the higher aspect ratio, the higher span wise result in a higher thrust generation. And they are quite in phase, only a small shift here, which might due to different acceleration level of the wing. Also, this 3 flow structure from the on-wing measurement of different wing is shown here. We can see the structure topology is quite the same, only different in the magnitude. Besides of DelFly 2, we also did some measurement on DelFly Micro with SIM setup. DelFly 2, we only measure the half of the DelFly since we assume it's a symmetric configuration. But for DelFly 2, we have a top clap and fling. That will result not a symmetry, not a symmetry. It will result a complex vortex structure. And from here, we also reveal this U shape shed by the clap of the wing in the end of in-stroke, and also this arc shape shed due to the out-stroke. The flow topology of DelFly Micro is quite the same as DelFly 2. Here is for different phase. And also, we also compare the different flapping frequency and the different wing aspect ratio. They are nearly the same flow topology, but only different in magnitude. Also, it's time to wrap up this research. That 2 thrust peaks different in magnitude was present in each flapping cycle. The lower one happens at the mid-in-stroke phase, while the higher one occurs at the beginning of out-stroke. But in DelFly Micro, it's the opposite way. The higher one happens during the in-stroke and lower one in out-stroke. And the first 2 harmonics of force spectrum are aerodynamically related by the vacuum test. The leading edge vortex developed during the hovering flight with DelFly have been confirmed to be more major aerodynamic feature that allow DelFly to stay aloft, as well as flexibility of the wing. The fling has for DelFly 2 only, the fling has the fundamental role of creating an inrush of air between the wing and thus enhance the generation of the leading edge vortexes. By the 3D reconstruction of the wake of DelFly 2, we find 2 very predominant vortex structure, a U shape and a knock shape, happens during in-stroke and out-stroke, respectively. Well, the effect of the flapping frequency and the wingspan, the different flapping frequency and wingspan also give the similar flow topology. They are only different in magnitude. And the higher frequency and aspect ratio will just produce a stronger vortex structure, but they can bring more thrust. And yeah. Okay, thank you. And
questions?
Yes.
Very interesting presentation.
Mm-hmm.
Your name is not because.
Yeah.
My question is regarding the vacuum test.
Mm-hmm.
The wing do not deform the same way in vacuum.
No, it's quite different. It's quite like a waving
Shuanghou,
shape.
can you repeat the question for the?
Okay, so your question is, in the vacuum test, the wing didn't deform at the same way as in air.
Yeah. Is that a good representation of the whatever that you measure in vacuum? Is it you're trying to minus off the inertial part of the measurement, right?
Yeah.
So is that still a good representation of the real flying condition?
Yes, I think so. And the vacuum test for us is only to identify the difference between the aerodynamic effect and also the inertial.
So it's not used for a correction,
No.
but it's just used to see which harmonics are certainly not related to inertia effects.
Yeah.
Other questions?
So-
You mentioned about a creaking thing. Is that just to reconstruct the wing?
Yeah.
Structure
Yeah.
from
Yeah.
Isn't it more simple than just build up and then just need to go to that filter because it's dissipative?
The question is, in the creaking interpolation is used for reconstruct the wake, but why just use different plane? And
My knowledge that algorithm is very dissipative. That means you're going to lose all the small scale.
yeah, for sure. By creaking, we definitely will get rid of some small structures, and there is also smooth function inside the creaking. That is, as we see it, we also use the temporal integration based on the Taylor's hypothesis. That means we use only one measurement plane and different time to interpolation. And from the results we found, that it's quite the same. So we think the quick interpolation is quite acceptable in our measurement.
There was a question in the front.
Oh, sorry.
During your experiment in the vacuum, what was the frequency of the wings?
The wings we tested from 10, 11, 12 until 14. That one is 12 hertz. Yes, they all give the same story. The first two harmonics is predominated by the aerodynamic. The rest from third is purely, it's not purely, it's less affected by the inertial.
And one more question.
Mm-hmm.
In your experimental setup, how was the area of interest decided upon?
For
You had 21 centimeter by 21
Yeah.
centimeter. How was that decided upon?
the wing flap is around, the wing length is around 14, the half span, and we can only capture the half of the wing since it's a symmetric mechanism. And 21 we decide it's, I think it's already 7 centimeters away from the wing, and we think that might be quite enough. But also in the post-processing, we didn't find any structures involved in like 20 centimeters. That we also see the results directly after the measurement. If there's some like chaotic flow there, then we will increase the size, but fortunately we didn't find that one. Yeah.
There's a question up there.
Yeah.
For the force measurement or the diffraction that you have showed, did you use some filtering, or are those the raw data that you measure?
I will repeat the question since you said in our force measurement if I use the filtering function or not. Yes, we definitely use the Chebyshev 2 low-pass filter.
Okay. And
Yeah.
what was the cut frequency?
The cut frequency is we keep the first two harmonics since it's aerodynamically related. And after that, we just cut off all of them. Yeah.
I think then this brings